So next we need to talk about measurement and numbers and what they mean when and all of that good stuff. So let's start by defining the fact that there are two different types of numbers that you'll encounter when you do calculations. The first is an exact number. Exact numbers are things that, honestly, they're exact. So like there's 12 in a dozen, or a foot has 12 inches, or let's see, in a package of 10 pencils, you have 10. It doesn't always have to be 12. We use a lot of 12 though, at least in the US. This is stuff that you use all the time. Then we have things that are called measured values. Well, so these are things that you determine in an experiment through observation. And when you take a measurement, you want to make sure that it's both accurate and precise. What in the world does that mean? You may think that those two terms mean the same thing, when actually they don't, as far as science is concerned. So the term accuracy, or if something is accurate, basically says how close is it to the real, actual value. So if the real value is 2 and you got 5, that may not be very accurate. But 5 is more accurate than 10, but 5 would be less accurate than 3. So you want to try to find the value that's closest to the actual value. That makes sense. Now, precision actually means how much a measured value is close to other ones that are measured as well. It has nothing to do with, is it right? It just has to do with how small of a gap is there between the numbers that you've actually measured. So let's take these bits of data. In this first example here, we have 1.24, 1.21, and 1.27. That looks pretty accurate. It looks pretty precise also if our measurement should be 1.25. That's pretty good. We could get another data set that looks like this. That doesn't look very good. The numbers are pretty far off from that 1.25, and there's a big gap in our data. So what do I mean by that? Is that 1.57 and 2.95 are a little bit further away from each other than what we really want to have precise data. And then here we could have something like this. These are accurate values. They may not be very precise. In other words, they may not be as within a narrow window as what we found in our first example that was both accurate and precise. But in the long run, that's still pretty precise. So these are things that we have to keep in mind as we move forward. It is absolutely necessary, though, to know how to obtain measurements that are observed in the laboratory that are both accurate and precise. And there's a way that we should go about measuring things. There's a way that we should go about recording our data. So you have to read information carefully, okay? You have to read what you are given very carefully. To take precise measurements, you have to take in all of the possible data. And sometimes that means that you have to estimate the last number. And by the way, did you know that if you put something on a scale, that last number is often an estimate? Because you know how it says plus or minus 0.02? Well, that's telling you how precise that instrument is. It's telling you that there may be a little bit off in that last number. And so that's something to be, to consider as we're moving forward with our data. So let's say we're trying to measure what we've got here. And this is our ruler. And I'm going to measure this line right there. And you're supposed to measure the line. Well, first of all, you have to make sure that this is starting where that instrument starts, and that you're not measuring, say, at the 1 or the 2.5 is where you're starting to measure whatever it is. Okay, good. Once you know that. This instrument measures within a centimeter, but it has no other marks on it. So do I say that it's just 2 centimeters? Well, I think that you all can tell that you can say a little bit more than just 2 centimeters about this, because here's where my actual line comes to. So what you need to do as an observer that's writing down your measurement is you need to estimate to one more tens digit than what's provided for you by the hash marks. So let's say that we're going to say that this is about 2.2 or 2.3 centimeters. That's probably a good estimate of the next tens digit. That's okay. You should estimate one additional tens unit beyond what the markings are shown. And see, in this example, we start with a ruler that has many more hashes on it. So this ruler actually defines where a tenth of a centimeter is. So again, we start where the 0 is, and we can see that the line is going to come about right there. Well, again, you can now see that this would be 2.1, 2, 3, 4, right there. And I can estimate to one more tens digit. So I'm going to estimate that this line is coming in between the 0.4 and the 0.5. So let's say that my estimate is about 2.45 centimeters. That's a good estimate. We can do that and see how the data is more accurate, or actually it's more precise because it's got more information in it than we had available to us with the other ruler that had less precision in it. So your instrument sometimes makes a big difference. Something to note, when you're taking measurements of liquids, you use a graduated cylinder. That's what the piece of glassware looks like. We'll talk about that more in lab. You need to read the bottom of the meniscus. So what that means is, you know how water forms this little blurb right there? The bottommost point is the one that you actually are reading. The bottom of the curve right there, okay? So let's say that this reading would be about 1.4. Now, something to note about graduated cylinders is that between here and here is 1 milliliter. So say if you had a measurement right here, it'd be like 0.5, right? So make sure you look at your scale on your graduated cylinder so you know exactly what it is that you are measuring. So as I was saying, that means that the precision of your measurements depends on the tool that you're using. It depends on your device. Not all measurements are the same, and therefore not all data is the same. When approaching things in chemistry, your data cannot be more precise. Let me switch that. Your calculations may not be more precise than your data. And that's why we need to figure out what data is most reliable or most significant. So let's talk about what significant numbers are. There's a way to define how many significant figures each data point has. We start by simply saying all non-zero numbers are significant. Anything that's 1 through 9, yep, it's significant because we know for sure that somebody measured that. Zeros are the hard thing to figure out though. Zeros that are between non-zero numbers, like this guy right here, he's significant because I know that somebody measured something after him, and so I know that he's good. We know that he's good. But zeros after non-zero numbers are assumed not significant unless there's a decimal point. If there's a decimal point there, all the zeros that are after actual non-zero numbers are significant. Here's what we mean by that. In this number 1230, well, this 0 right here is not significant. He's just a placeholder. We don't know for sure that that was measured. If there was a decimal point to the right of him, we would know that he's measured, but we don't know that right now. So we can only say that this has 3 significant figures. See how adding this little decimal point right here, though, that says, yes, everything above here was absolutely significant. And it's like you declaring, that is significant, everything before it, right? So everything here would now be significant because that decimal point declares it. And if you keep going and have numbers after that decimal point, it's still significant because it tells somebody that I measured it to a precision. And this is how many numbers I believe are right. Okay? Now, the same way we can have numbers after whole numbers that are kind of placeholders, we can have zeros preceding non-zero numbers, and those cannot be, those are not significant as well. So here's what I mean. See this number down here? These 3 zeros are just holding a place until we get to the 3 significant figures here. Same thing here. These are just holding a place. So if I were to write these last 2 in scientific notation, I wouldn't put my zeros in at all. As a matter of fact, I would say 3.29 times 10 to the negative 3. Because they're not significant. That is one way to sort of also tell if you have a significant number or you don't have a significant number. If it's not going to be involved in the scientific notation, then it's not significant. Okay? Now, we'd probably need to practice this a little bit, but I have a little bit of more information that I'm going to give you before we really start practicing too much. When it comes to significant figures, there's ways to calculate things as well. Better yet, when it comes to calculations, there's ways to report our data that's the best practice. That's a better way to put this. When you add and subtract, what you have to find out, like this number set that I have down here, is which of our data points gives you the least number of tens digits. Like you see right here, this only goes to the tens. This goes into more detail, so does this. But we can only be as accurate as our least reliable data, and that's this guy because he has the least reliable data, okay? So though you may add things together and get this big number, we have to round to where we only use the tens digit. And there are some people that will tell you to do fancy things with rounding. Let's just round. 5 up goes up, or 5 and up goes up, 4 and below goes down, okay? Let's keep it nice and simple. And when we do multiplication and division, we count things a little bit differently. It doesn't have to do with how many tens digit. We actually have to count how many significant figures we have. And the data point with the least number of significant figures tells us how many significant figures to report in our data. So this 21.0 right here, that has 3 significant figures. This guy right here has 5 significant figures. And this guy right here only has 2 significant figures, which means that our data, once we take it, needs to be rounded to only having 2 significant figures. Okay, so I first put that in the calculator and get this big long number. Honestly, it goes way longer than that. I just didn't write it all out, okay? And then you have to round to only 2 significant figures, which means I've got to round to just getting this. So your final reported value should be 130, or you can write it in scientific notation as 1.3 times 10 to the second. Sometimes scientific notation helps when it comes to these things. One thing to note though, you know those exact numbers that we started talking about? It's really nice that they do not count when you're trying to determine values of significant digits. So an exact number like 12 is equal to 1 dozen. Well, guess what? I don't have to worry about the fact that he's significant figures, because he's not. And that means that this guy dictates everything. 392 tells me 3 sig figs. I do the calculation. I get something that looks like this, and it tells me that I need 3 significant figures in my final answer. So wait a second. If I do that, that should be 4,700. I can't actually write that because that's only 2 significant figures, and I need to determine something that's 3 significant figures. In this case, you really need to report things in scientific notation, because that's the only way to show that I've got 3 significant figures and that 0 counts, but the other 0 does not. Right? So one of those zeros counts and the other one does not. So that's sometimes the only way to show that. We will practice this more in class. Again, there are so many examples online. I highly encourage you to practice these problems. Thank you very much, and let me know if you need anything.